Hey guys, welcome to Centripetal Force. So it's the fourth section in our study of uniform circular motion. And so let's jump into this here. So, first thing we have for an object to experience uniform circular motion, it must experience a centripetal acceleration towards the center of its circular path. So, that is the green arrow. That's that centripetal acceleration that's there. And it's always perpendicular to the tangential velocity to that v right there. And so we know that the acceleration, the centripetal acceleration, is given by v squared over r, where v is the tangential velocity, r is the radius of the circle. And what does that tell us about the force acting on the moving object? Well, what we studied was that a net force will always act in the direction of the acceleration. So, if Newton's second law says F equals ma, and for an object in centripetal motion, there must be a net force acting on it directed to the center of the circle. So the net force is mass times acceleration. So the centripetal force, that center pointing force, is calculated by using mass times velocity squared over r. And so we'll have some demos and stuff when we get into class on the next time I see you guys, I think this week. But we'll kind of understand what exactly that means. So for centripetal force, remember earlier we learned that an unsupported object near Earth experiences an acceleration towards Earth's center of magnitude g, which is 9.8. And then we use that information, or Newton's second law, to learn about the object's mass or motion. So remember, we would say a force is a mass accelerated. So now that we know if an object is in uniform circular motion, it has an acceleration directed towards the center of the circle with a magnitude v squared over r. And we can substitute that into v squared over r to determine what the net force on the object is. So this equation doesn't describe the source of the centripetal force, or even that there's just one force acting on the object. I could have multiple forces on the object. This just says that the sum of all of the forces acting on an object traveling in a circle must have the above magnitude and directed towards the center of the circular path. So we're going to look at things where that is provided by gravity, tension, friction, etc. And any type of force can make an object move in uniform circular motion. So let's run through a couple of examples. I'm going to go through these kind of quick. You can pause the video. Here we have an object, a 12 kilogram object, 8 meters per second, moving in a circle with a certain radius. So we know the givens. And the question is asking for the net force of the object. So F equals ma, or F equals mv squared over r. We substitute everything in, so we get a net force of 48 newtons. And this is directed towards the center of the circle. So if it's moving in a circle, the net force is always directed towards the center of the circle. Second example here. Want to know what its velocity is? So here's my givens. I'm given the mass, the force, and the radius. And so what I did here is I first plugged in our original F equals ma, or F equals mv squared over r. Solved for v, and so there's the algebra to solve for v. Then you plug everything in, and hopefully we get 3.3 meters per second. That is how fast, or the tangential velocity of that object using that given information. And the next few examples are kind of the same thing. We're just rearranged what we're given. Oh, sorry, I missed some animations here. But you guys get the idea here. We solve for r. So on the left-hand side over here, we end up solving for r first, and then plug everything in to get an 18 meter or 18.2 meters into the resulting equation. So here's something a little more interesting. The first artificial satellite to orbit the Earth, Sputnik. I don't know if you guys have heard about that in Mr. Little's class or not. But it was about 84 kilograms, and it orbited once every 5,900 seconds, almost 6,000 seconds. And it's at a distance of 6.4 times 10 meters to the second. And so what we do here is we have our given information, but we have this weird way to say this now. So notice we have the velocity, and we have this piece right here. So this velocity squared is 2 pi r over t. Remember, that was the way we calculated the velocity. So it looks funny. And then this secondary step right here, once again, it kind of looks funny. But it's just using the same thing, making sure we understand how a little bit of the algebra works. That t goes down here to the bottom. I have r squared over r, so that's why I have that 1r that stays there. So make sure we understand the algebra there. Substitute everything in, and we should get about 610 newtons was the amount of gravitational force acting on it, which isn't a lot. It's kind of an interesting idea when we think about it. So the last question is we have the frequency, and what we're looking at is a ball being swung around in a circle. And so we have our givens here. Once again, we have frequency, and this one gets kind of weird very quickly. The second step, or the third step here, is where it gets a little crazy. And so without spending tons of time just talking about this right here, I want you guys to figure out how to get V out of this chunk in here. And once you do that, you'll be able to see pretty clearly where that comes from. So how to get V to the 2 pi r f. Once again, just remember the relationship between f, frequency, and period, big T, and that should clear everything up for us. This step here is just this chunk squared, and the rest of it is just kind of an algebra thing. So there's multiple ways to do this question, but I thought it was kind of interesting to do it this way, so we kind of left it there for you. We plug everything in, and we get about 6,500 newtons worth of force, making that object spin 25 hertz. That's 25 times per second. So that's really quick. So I want us to kind of think about what happens to that force the faster you spin that, and that'll be a lot of what our next activities will be encompassing. All right, so here's our assignment. There's a Google Classroom form that we can do, and then the problem set listed on my Trinity. Let me know if you have any questions. Thanks for watching. I'll catch you guys later. Bye.